So what we discussed last class, we discussed the mechanism of spatial filtering, where basically we define a mask or a filter, and that mask is defined around a neighborhood of a location, and at every location we compute the sum of the products of the corresponding term of the. So at every pixel, at every location, we basically compute the sum of the products of the filter and the image pixel values, and that will be the transformed pixel value of the image in the output image basically. And this process is repeated for all the locations. And we started with an example of a smoothing filter, and how smoothing filter, what does it do when you apply a smoothing filter? What does it do? So that everything that any filter will do, that depends on the coefficient values. But what is the effect of the on the image? It smoothen the edges. So whenever there is a sharp transition here, for example, so for example here it's going from 0 to 90 value, that is a sharp transition. So instead of that, now the transition will be more, sorry, so instead of sharp transition as in this image, now the edges will become more smoother kind of thing. And if there are occasionally outliers which can be treated as noise, their effect can be reduced to some extent by a smoothing operation. And at the edges we have to do some kind of a padding or replication, so that we don't have to treat them specially. And instead of a box filter, we discussed that we can use kind of a Gaussian filter, which will be kind of a weighted filter, or which will do kind of a weighted smoothing. And you can define any Gaussian filter depending on the size and sigma and all that. And the more the sigma, the higher will be the greater will be the extent of the smoothing on the original image. So we'll see more example of smoothing later on, but I want to highlight something here, that this mechanism that we have discussed of spatial filtering, taking a mask and then correlating at every location with the image values and getting output values as a sum of the product of the corresponding terms, that can be used also for something called template matching. So in fact, in the early days of image processing, this was the only method which was used to detect or identify interesting objects or locations in an image. So what we do here is basically, we can, instead of we can take a template of the object that we are trying to look into an image. If we have a template of that, then we can actually do the same process. We can do a same spatial correlation of that template with the original image, and the result will be that wherever the product the sum of the product score will be high, those locations will correspond to locations which match with the template. And why that will be so? So if you want to understand mathematically, we can represent this correlation operation. So this was the correlation operation in equation form. So so this was the spatial filtering process in the equation form that we have represented. If we can think of this also. So let us say the W filter, let us say it has W1, W2, W3 and so on, and similarly the corresponding image location as f1, f2, f3 and so on. So we can rewrite this in a more simpler form as w1 f1 plus w2 f2 and so on, because we will be basically doing the corresponding things. So if we treat w and f as a vector with the components as w1, w2, w3 and so on, then this is something same as a scalar dot product of those two vectors, isn't it? You recollect the scalar operation between two vectors. So we can write this C as simply a scalar dot product. So let us say in two dimension, if there are two vectors, let us say f and w with certain at some theta. So if we take a scalar dot product, normally the scalar dot product will be the magnitude of w and times magnitude of f and cos theta. So when will this value will be maximum? When theta is 0, that means when w and f are aligned, or that means they are kind of a similar vector, then the correlation factor will be the highest, isn't it? So this score will tend to be high when the w and f are kind of a matching, have a matching value, isn't it? So for example, if w1 has all zeros and wf are all ones, the score will be 0. Similarly, the opposite way, if f has all ones and w has all zeros, score will be 0. Whereas if both have half, let us say, the score will tends to be little higher side. Other way, if you want to understand this thing, you can also, so for example, let us say if you subtract w minus f, if you take the sum of square difference, you want to take the absolute difference of two, the difference between w and f, and normally we would like to take an absolute value, but let us say in terms of, to get rid of the square, the sign thing, we'll just square it. So this will be basically, so isn't it? So when will this difference between the two will be smaller? When this will be higher, then the difference between the two will be smaller. So in both way we can see that the the filter w and the corresponding look sub image of f will tend to match if this score is going to be higher. If the score of C, this correlation score will be high, then probably they will have some similar appearance. So we can use this thing for doing kind of a detection, for a detection purpose. So for example, let us say in this image we were interested in finding a region of containing object of this shape. We can take this shape region as a template itself as our mask, and use this mask and do a correlation operation, spatial correlation operation on this original image. And if we see the intensity, the score, if you plot that score values in the intensity, so the higher score will be white and the low score will be black. So you can see the wherever this template is tending to match the original locations, there all those locations score is little towards higher side, and the peak, the maximum score is when it is exactly matching this one. So you can see this at this location the score tends to be the highest thing, and there are next higher location at other location, because some of the appearance here is also similar to the template, whereas at other locations like this background locations the score is not so high. So this is on a toy example. Yes, what? Not multiply, the process that we defined, the spatial filtering process. So take this mask, put at every location. So take this mask, put on the first location. So you will, whatever that value will come, you will replace this intensity value with that value. Now shift this by one row or one column. Shift this mask by one column. Then you will get the output value for the next location. Yeah, both might be of different sizes. So what do you expect? Will it give a high score or no? So if the size of the object, let us say size of the template and the size of the object in this image is different, what will you expect? Hmm. So as your intuition is right, only when the object size in this case will match, then only you can expect to get a higher score. If the object size is too different, you won't get a good score. Whole scene was this whole scene was on the black image. Then what is the problem? It's a binary image you are saying. Huh. Oh, it was totally black image, and you applied this kind of so then you will get some so then there is no pattern here. You may get some score here, that depends on what values, but probably it will be uniform because it is a uniform image. The score will be uniform all around. It not be all white, it will be some value, but that value will be a uniform value because there is no pattern here. It's a uniform pattern, so at every location you are having the same values, so you will get a uniform score across everything. I'll take more example, it will become more clear. So template matching is not a very is not an ideal thing, but I'm just telling this is one application of this spatial filtering can be done for doing template matching. Uh, First of all, a simple correlation is not always sufficient, because if you do a simple correlation, let us try to understand that. If we do it, I'm taking just an example of a 1D signal here. So let us say I have a one dimension filter of values 375 and applying it on a 1D image or a 1D signal with some arbitrary values. And if I calculate the sum of the product and substitute the values here on the boundary, I'm just replicating it. So 3 will be replicated here and 2 will be replicated at the end, kind for the padding purpose, and I'll get this score. So what is the problem here? So where do you think this should give the highest score ideally in this? So 384 is the best match, which is coming closer to the to the template that we have taken here. So ideally you should get a high score here, and you are getting a highest score here, but you are also getting a high score at some other locations like this and this. Why here? Why you're getting a high score here? Magnitude is high because the correlation that we are taking, the magnitude of the underlying signal itself is very high. So whether or not they are matching, but the magnitude itself is high. So that's why it is giving a high score here also. So if you do a simple correlation, it may not give you the right response. So what should we do? Divide by. So you can normalize by magnitude. So that is one option. So there are two options. One is instead of doing a correlation, directly do the sum of square difference, s fw minus f ka whole square. Take the sum of the square difference itself to see the similarity. You want, basically your purpose is trying to see how similar they are. So if you directly take the sum of square difference, the value that you will get here is, in this case the score should be low. If it is similar, the score should be low. So you can see at 384 the score is the minimum one, and all other, the next highest location is, the next close location is 13, but the difference is quite high. So you will be able to clearly able to pick out the region of match by taking the minimum value. So this is one operation, but this sum of square difference, first of all you have to do squaring and all that. That is little computationally problem. But there is a better operation which is generally preferred. This is called normalized cross correlation, which Gayatri told that we can normalize the correlation score. We do the same correlation operation, but you divide by the magnitude of both these functions, the W function, the filter, as well as the image function. So this is the magnitude of that. So now the result will be between 0 and 1. Now all the scores will be between 0 and 1, because our images, assuming our images are an unsigned int, if they have negative values also, then that can go otherwise. There is a slight difference that we can also do here. We can to get a better range, instead of 0 1, we can stretch the range little bit. We can get values between -1 and +1 for better precision. If you subtract the mean from the WNF, so for each, so you get the correlation as W minus its mean. Basically, I'm just taking the let it be a vector kind of thing, and similarly, so this is mu, basically the mean value. So if I subtract off the mean, then the correlation scores will come from -1 to +1. So that this is only basically you will be able to stretch the range. Sometimes that is useful because otherwise the values become too close. So to be able to pick out a distinct peak becomes a difficult thing. So it's better if you can do a stretching. And that function is that operation is implemented in MATLAB. There is a function called normalized cross correlation 2. If you don't take the 2 one, if you just take normalized cross correlation, it will do the normal one, that is this one. So there the output will be between 0 and 1. This 2 1 is basically which will subtract the mean also, so you will get a little higher range. Okay, let me just show you what will be the on the same image, that on the same example that we were taking. If you do a normalized cross correlation, the output that you will get will be something like this. So is it giving a good output? So around 384, you are getting the highest score. So that is so that is good. At least you got a highest score for one location, but you also got a high score which is quite close to this at this location. So here I am replicating it, so this value will be 2. So I am getting a very high score here also. Why it is justified? Why 122 is close to the pattern that we are matching 375? I think 375 what we took, because we are normalizing it. So let us say if we scale this pattern, multiply it by 3, will be 3, 6 and 6, which is quite closely matching this thing. Is quite closely matching this pattern. That's why we are getting a high score here, which is doing the job, because that is what we were doing. We are normalizing it by the magnitude, so it is doing the right job. And sometimes we do need that thing. So let us say if the intensities are just scaled up by, because in a different environment you took the image and the brightness was scaled up and scaled down. So if you do a normalized cross correlation, still you will be able to get a match, even if even if the intensities values have been scaled up and down by a constant factor, you will get a good match. And that may be a desired attribute or a desired behavior that we would like by doing this kind of an operation. So in MATLAB, if you take this image for example and use this function, I've just shown the output here. So here I've just taken the mass as one sub image of this original image, and if I take that sub image as a filter, as a template, and do the correlation on this, so you can expect the maximum value. You have a distinct peak at the location where this will have a closer match. Of course, it may not be so. Template matching is quite tricky. Sometimes you get a very close peaks, and to pick up a distinct peak is little difficult thing, especially if it's not a simple binary image. If it is like a color image, or if like this thing, doing template matching is not a robust operation, but it is some preliminary operation by which you can do that. So just an exercise for you here. Let us say we want to detect a straight line in a binary image, either horizontal or vertical straight line, a single pixel thick straight line in the background of 0. Can we design a filter or a mask and do a template matching to detect straight line? So for horizontal line, let us say if you want to detect a horizontal in an image, you are given only a binary image. There may be a straight horizontal line of 1 pixel thick straight line anywhere in the image, and if you want to detect those locations, can we do so what will be our mask? So let us design a 3 by 3 mask. What value should we, what should be the coefficient values? Hmm? Hmm? So here assuming black is 0 and white is 1. So what value should we give here? 0 0 0 for horizontal, 1 1 1 0 0 0. Is it right? Will it work? Will it detect straight line of 1 pixel thick straight line in an image? Will it give the strongest response? So let us say you are not having just a single, you are having a not a single pixel thick line, but a, so these are all 1 pixel thick line. This is not a line, it's a block of 1 pixel and background is 0. If you apply this mask, what values you will get? So wherever all these are zeros, what will be the value? Value will be 0. Let us say on this boundary pixel, of 1, the first row will be 0 0 0. When this is aligned to the boundary pixel, you will have 1 1 1 3, and this is 0, so the result will be 3. If you move slightly down, go to the next line, let us say the next line here, what will be the value here? Again 3. If you go further down, again 3. So it is going to give 3 line the values of 3 for across all this entire patch of 1. So if you have a single pixel thick line somewhere here, and if you have this entire patch of or entire block of 1 somewhere, you will get the same response. So you will not be able to distinguish whether it is a whether it is a single pixel thick line or some patch of, isn't it? You will get the same correlation response. So I want the highest response for just those locations where there is a single pixel thick line, and at every other location the response should be less than that. So how should we modify this coefficient values? So how should we modify this filter values? Hmm. So I'll just give you an answer. Can you justify? Now you got done. So if you take this thing, now this is going to give the maximum response for only a single pixel thick line. At every other location, it may give a non-positive response, but that response will be lesser than the response that it will give for the single pixel thick line. So for horizontal line, so you can notice the sum of these coefficient values is going to be 0. So at every other location where there is a uniform patch, it is going to give a kind of a zero response, and wherever there is a single line, it will give a highest response of 6. So from 0 to 6 it may give different response at different locations, but the maximum response will be for straight horizontal line. Similarly, for vertical line we can use this mask. For a 45-degree diagonal line, inclined line, we can use this mask, and for minus 45 or line in this direction, you can use this mask. So an example of that on this image, binary image, let us say on this binary image, we were, let us say, interested in detecting a 1 pixel thick line with an angle of minus 145. So this one is the line that we want to detect basically, because this is a small single. All other locations, these are, for example, this is a vertical line, but this is not a single pixel thick line. This is also a same line at the same angle minus 45 degree, but this slightly thicker than a single pixel, and other locations they have a different angle. So if you apply that mask on this, the response that you will get will be something like this. It is basically, as you can see here, it is giving the maximum correlation where it exactly matches the template. At other locations, wherever it is multiple thick lines, so probably at the beginning of the line and at the end of the line, it is giving slightly higher, and in between some values. At other locations, it is giving some response because it will be doing some, it will be partially matching, but that score will not be that high. So if you threshold it, so after this image, you will if you have to detect the actual location, you have to do a thresholding operation with the maximum. So take the max of all this value and choose a threshold slightly small than that max, little bit smaller here. So this is the result of thresholding with this image by the maximum score of this image, or maybe slightly smaller than maximum score. So these are the locations which have surpassed, which have basically filtered out. So this is the one, this is the exact location that we were looking for. These locations also we have got some things because the angle is quite closer to minus 45 degree, and these were all single pixel thick line. Okay. What if we are doing a general purpose template matching where scene may have, we may have a template which may not be exactly similar to the object that we are looking for. For example, in this case, we are trying to detect a vehicle or a car, and we have a template of some car, but that car may not be the same as this car. And if we apply this template across this, do you think we'll be able to detect this location? Hmm. Yeah. So we'll later on see the better approach will be to extract some distinguishing features which may be essential part of that object, like tires or the windows and so on. So that probably will cover towards the later part of the course. But here we are only discussing about simple template matching. In this case, let us say if you take this template itself and on this image itself, and you do a, what do you expect? Will you get the peak score will be somewhere around this car or not? In this case, it will match. It will tend to match because if you see the scale of the size of the template and the overall appearance, it has two tires which have similar appearance, windows similar appearance, which is quite different than any other background here. So in this case, it is going to do you will be getting a probably a closed response, a maximum response somewhere in the center of this location. If there are multiple objects uh, of similar appearance and similar, then it may not do, then it may get confused. So template matching is only will only help you as long as the general appearance, the scale and size of the object, the orientation is right. If you change the orientation little bit, if you change the template little bit, For example, in this case, the car was slightly tilted rather than straight, then you will not be able to get the high score. So template matching is just a very crude thing. It will fail in most of the scenarios, uh, but still it is a very powerful thing. If you are working in a in a constrained domain, if you know the template, if you know the object informations. So let us say the same quiz for you. In which of these following case do you think template matching will work? In the first case, let us say we are trying to detect a structure of kind of a house which will have some patterns like lines and windows and doors like this. Another image which may have faces of people. Another image where you may have these icons of in our Windows operating system like folders, files, and other icons. And maybe another image is kind of a medical image where you may have these tissues and other things. So if you are interested in detecting these objects or these regions, in which case do you think template matching will work and not? Hmm? So third will match the best because probably the size of these icons, the scale, appearance, everything will is constant. Is doesn't have so much variability. So these will be able to detect will be detection will be good for template matching. What about faces? Faces have so much variations, so you cannot have a single template which will represent all faces. What about this? Hmm? It will also not work ideally because again I say the orientation, the scale, size, and all things will vary. So it's very difficult to get a template which will even if you have many templates, still it's very difficult to do all that. Huh? So okay, so let us move forward. Hmm? Okay, so till now we have the operation that we have talked about was just correlation. There is some similar operation which is called convolution operation. In fact, most of the term in image processing literature for all these operations, generally the convolution is a term which is used in most of the literature. There is only slight difference between correlation operation and convolution operation in terms of mathematics. The difference is that in convolution operation, basically the operation is defined like this. So basically, you are flipping it. So uh, you will have to flip the signal or the mask by 180 degree, rotate it by 180 degree, and then do the correlation. So generally, the convolution operation is represented by this asterisk sign. So the difference is only a simple difference. You can either rotate the mask itself or the filter or the original image itself. You just flip it by 180 degree. Just take a mirror image of that signal and then do the correlation operation. In most of the time for us it won't matter because normally the filter that we normally tend to choose is almost a symmetric. So if the filter is symmetric, then even if you reflect it, it is going to have the same effect. And most of the useful filters that we use, they are almost symmetric filters. So it doesn't really matter whether we are doing a correlation operation or a convolution operation. But in case if the filter is not symmetric, then the term of correlation and correlation will have a different notation. But generally, these two terms get interchangeably used in image processing literatures because of the reason that most of the times the filters that we use are kind of a symmetric filter. But there is a good thing about convolution operation. Convolution operations have many nice properties which correlation may not have. Some of the properties we'll discuss here, and some properties we'll discuss later on when we go into frequency domain. Convolution operation is mathematically commutative, associative, and distributive. And of course, for this you'll have to go through a mathematical proof. I won't give it here. You have to trust me that. So if you don't trust me, you can look into the book and go through the derivation operation. No, the proof won't come. If I'm not discussing, it won't come. So convolution operation has nice property. As I said, it is commutative. Correlation is not always commutative and associative. It is distributive. And conversion of a filter with an impulse function yields the same signal. So impulse function is nothing but a very high value at just that single location. So I know if you're talking in a 1D domain, an impulse function is basically a whose spread is not large. Spread is just at particular point. It has a very peak. Almost the signal tends to infinite. It is most of the time used in signal processing. For our image context, it's not so useful. But the thing is that if you take this impulse function and convolve with the filter, you will get the original. It will give the original image itself. It won't change the output. Anyhow, so so for one illustration of the property of convolution, so let us say if you take a Gaussian filter and if you convolve that Gaussian filter with an image, and let us say you convolve it again 2 times, then the effect will be same as convolving the original image with a larger Gaussian filter. Why? Because we said the convolution is associative. So if you first convolve with one filter and then convolve with another filter, is same as you first convolve the two signals separate together and then convolve with the original signals. And yeah, another thing property, Gaussian function. If you convolve a Gaussian function with another Gaussian function, you get a Gaussian function itself, but with a larger spread. The variance will increase. So the thing is that for as far as utility purpose, uh, if you want a higher smoothing, instead of multiple times doing a convolution operation, just choose a Gaussian filter with a larger sigma. And we have already seen that if you choose a Gaussian function with a larger sigma, so that will be more efficient in terms of operation. You have to do just a single convolution operation rather than doing two convolution operation. Another utility of convolution operation is that if you are worried about the time complexity, because sometimes the time complexity may be a problem. So if you are doing a convolution operation, what is the magnitude of the operation? So if let us say image is of size n by n and filter is of size w by w, then how many multiply operations you are doing? So at every location, filter is w by w, your neighborhood is w by w. So at every location you are doing w square sum of product operations, and total number of locations are n square. So that means the order of n square w square operations we are doing for doing this spatial filtering process. And in case if filter is larger size, this things is going to become little. We will have to a little bit worry about this computational complexity. In fact, the CNN, the convolution neural network that we nowadays use, it has the computation complexity of that is little higher side because of this thing only, because the convolution operation itself is bit bulky operation. So the one way of improving this is you can try to separate the filter. You can sometimes the mask that we are trying to convolve with can be separated into two one-dimensional kernels, and then in that case they are called separable kernels. So what it basically means that if a 2D convolution kernel can be separated into two one-dimensional kernels, so for example this smoothing filter, this 2D filter, you can get this filter by taking a column vector and a row vector and multiplying it. This will give you this filter. So you can represent our filter H as H1, which will be a row vector, and H2 will be a 1D column vector. Then if you want to do a convolution of H with F, it's same as doing, because our convolution operation is distributive, you can first convolve with H2 and then convolve with H1. So that means you first take the image, convolve with this 1D kernel, and then take the resultant output and convolve with this 1D vector. So will it save computation? What will be the, so cost of 2D correlations we have already seen, it is order of n square w square. In this case, what will be the order? N square w, isn't it? So there is a one order magnitude less. So if w is higher size, you can see if you can split the kernel into two 1D kernel, and then you can go for that. Later on we'll see if we can also go do this operation in frequency domain, because the nice property of convolution operation is in spatial domain, convolution operation becomes simple multiplication, point by point multiplication in frequency domain, so which is much efficient to do. So that we'll discuss later in when we discuss frequency domain. That is another way we want to reduce the computation complexity. We had seen this smoothing operation is good for noise removal, but it's not an ideal for noise removal. There are some non-linear filters which are more ideal for noise removal. They are also called rank filters or order statistic filters, like median filter, max min filter. These are called non-linear because the operation is not a linear operation in this case. So what is this max min filter basically, or median filter? Max min filter basically says that in that neighborhood, find the maximum value and replace the center value with the maximum value, and min basically says replace it with the min value. So why you may want to do this max filtering or min filtering? So there is a kind of noise called pepper noise and salt noise. Because of their characteristics, salt is a white pixel and pepper is a black pixel. So sometimes noise in an image looks like, so this is an example of an image corrupted by pepper noise. So these are when there are voltage fluctuations at some locations, so our voltage get trimmed either at 0 or at 255, then the result will be the image will be corrupted by this kind of a salt and pepper noise. So if you want to remove this, you can run a max filter on this image. This will get rid of pepper noise. Why? Because black is 0 and you are going to choose the maximum value in the neighborhood, which will probably be not the will be different than the 0 until unless your concentration of noise is so high that entire neighborhood is all black, which will not be for the most of the case. So if you go for a max filter, you will be able to easily remove all the pepper noise, and similarly with min filter you will remove all salt noise. But there is a side effect here. As you can see, if you are going for a max filter, white portion, so for example this black strips, these connectors chips, these are getting thinned, and similarly on the other side these are getting thickened, which is expected. So that is a side effect of doing this man and mid one. Sometimes if both noise are present, if both salt and pepper, both noise may be present at the same time in an image, then you can go for a median filter. In median filter, what you do? What is the median operation? So in that neighborhood, you sort them and choose the 50th percentile, the median, the middle value, or the middle rank value, and substitute by that thing. So this will take care of both salt and pepper noise, because what will happen, if there is a salt and pepper noise in that neighborhood, after sorting that will settle either at the bottom or the top, and middle values will be your original image values, and this will be that will be retained. So on this example, so let us say you have this ramp image where signal 1D signal, let us say this is value 1, 2, 3, 4, and at fifth location you have some arbitrary high value, let us say 20, 25, and then you have 6, 7, 8, 9, and 10. If you do a 1D median filtering operation on this location, what will be the output? So let us say a region of 3 if you choose. So here you will be having 2 only, here you will be having 3 only, here you will be having 4 only. At this location you will have 4, 20, and 6, so you will get a value of 6 here, and this location 26 and 7, you will get a value of, no, why 7? It will be 6 only, na? Oh yeah, it will be 7, okay. And then again 7, 8, and 9. So you can see the values will be closer to the original values rather than that. So good thing about this median filter is that it won't blur your sharp edges. At the same time, while removing the noise, if whenever there is a sharp transitions, because the edges represents when the objects change in the image, so the intensities values will immediately change. There will be sharp transitions, and we have seen in smoothing operation, when you took a smoother filter, this will it will kind of blur the image, blur the edges. Sometimes the edges are very important part of our image which we do not like to blur it. So in that case, if you can go for a median filter doesn't blur sharp edges. So that is a good property of median filter. Uh, that's why median filter is most, and this is a visual illustration on this image which has both salt and pepper noise. If you do an averaging operation, first of all, it has not got rid of all the noise factor is still there, because the contribution of those extreme outliers, they will still have some impact on the averaging operation. And also there is a blurring here, but you can see here the distortion is much less, as well as at the same time the noise has been significantly removed by using a median filter. But the problem is not solved if the concentration of noise increases. So let us say here the concentration of noise is 25% concentration. So this spatial concentration increases. Then if you do a median filter of, let us say, 3 by 3, you will be still be living with locations where the concentration is high. So probably in that region, in the 3 by 3 region, majority pixels were those noise pixels itself. So the median value, even if you choose the median value, that median value would still be so you can go for one more pass of a median filter. So there are two options: either do another iteration of a median filter, or straight away take a larger box. Problem with a larger box is, if you take a larger box, there will be a distortion introduced, because as you are increasing the neighborhood, it's going to have, it will going to distort the original image values, so on. So the result is being shown here. Same image, iteratively doing it by 3 by 3 times gets rid of uh, all the noise pixels. So if you can see in the original image here, you can see some speckles of noise still here. Here is almost removed, but still some locations are there, and this one probably has removed everything. But the same image I think we had shown earlier with Maybe I have not that image here. You can do by a 5 by 5 image to get rid of uh, there is a you can go for an adaptive median filtering algorithm, which will, as Shika has observed in last class, that different regions, depending on the characteristics of different regions, we can choose a different size of the filter. So wherever those locations where the concentration of noise is higher, we can go for a larger size median filter, and wherever this is less, you go for a smaller size median filter. And if you can design an algorithm which can intelligently do that, that you don't have to manually change the size for different locations. We have an algorithm, we'll discuss that in the next class, that's called an adaptive median filter, which will basically inspect the spatial density at different locations and accordingly adjust the size of the filter, and so that at the same time, while getting rid of noise, it doesn't introduce a lot of distortion. So it will remove very spatially test noise, but it will also reduce distortion at the same time. We don't have time, so we'll stop here, we'll discuss this, continue it here in the next class.